Differential and integral operations 5. Calculate the work done by following a straight line path from the Cartesian point 1, 1 to 3, 3 if the force exerted is given by x minus y ex hat plus x plus y ey hat. Can this force be derived from a scalar potential? Pick any other path that goes from 1, 1 to 3, 3 and calculate the work done. Well, first of all, on the Cartesian coordinate system, the differential displacement vector dr is dx ex hat plus dy ey hat. Now, if I take the dot product with the differential displacement and the force to calculate the work done, the force is x minus y ex hat, so this will have a non-zero component only for this term, so x minus y dx, and for this term it will have a non-zero answer only for ey hat dot ey hat, because ex hat dot ey hat is 0. Ex hat and ey hat are orthonormal vectors. And on the path we're supposed to follow, x is equal to y. So we're going to do this calculation. X is equal to y on the straight line from 1, 1 to 3, 3. All right. I'm going to call this path 1. All right. And then we can calculate the work done by the force dr dot f, that's the differential work done. This will be, now if I set x is equal to y here, this will become 0. This will be 2y dy, or x is equal to y, it will be 2x dx as well. So this is 2x dx. And now the integral from 1 to 3, 2x dx will be x squared, which will be evaluated between 1 and 3. So that therefore this is 9 minus 1, which is 8. So the answer I find on path 1 is 8. Now if I take another path, let's say that if I go from 1, 1 to 1, 3 first, and then 1, 3 to 3, 3, so along this second path with two segments, 1 and 2, on segment 1, I will have a dr1. I'm moving on the y-axis, so this is dy ey hat, dy ey hat. Y is changing from 1 to 3, x is fixed at 1, and dr1 dot product with f will be, so I have x minus y ex hat for the force, because x is 1, it is 1 minus y ex hat, and then I had x plus y, so it is 1 plus y ey hat. That's the force dot product with dy ey hat. And as for the second one, dr2, I have dx ex hat, because I'm moving on the x-axis from x equals 1 to x equals 3. Y is fixed at 3. So this is x going from 1 to 3. Y is fixed at 3. So the dr2 dot product with f will give me x minus y, which is x minus 3 ex hat, and x plus y, so x plus 3 ey hat, dot product with dx ex hat. All right, now I can write the integral on path 2. For the work done by this force, dr dot f, the first component is when y is changing from 1 to 3, 1 to 3, dr.f. So dr.f will give me 1 plus y dy. This ex hat dot ey hat is 0, so this will give no contribution. 1 plus y dy. And as for the second segment, x changes from 1 to 3. And here I have dx ex hat, so x minus 3 dx. So this will be x minus 3 dx. Performing this integral, I obtain y plus y squared over 2, y plus y squared over 2, which will be evaluated between 1 and 3. And then I have, for this integral, x squared over 2 minus 3x, which will be evaluated between x equals 1 and 3. So this will give us 3 plus 9 over 2 for the first term, and minus 1 minus 1 over 2. And here I have 9 over 2 minus 9. And then I have minus 1 over 2 plus 3. So what is the answer? 9 over 2 plus 9 over 2 will give me a 9. So this is my 9. And then I have 3 plus 3 giving me a 6 here. So these two giving me a 6. And then I have minus 1 over 2, minus 1 over 2, minus 1. So I have minus 1, and minus twice 1 over 2, which is minus 1. So that takes care of all the terms here. So this is 15 minus 2, which is 13. So my final answer is 13 for this path. Therefore, I find that the integral over path 1 for dr.f is not equal to the integral over path 2 dr.f. The work done by the force depends on the path taken. Therefore, F is a non-conservative force. It cannot be derived from a scalar potential. Now, apart from doing this work on two different paths and showing that they're not equal, there is an alternative way of showing that F is a non-conservative force. Let's check the curl of F. Curl of F. Curl F. This is a determinant. We have EX hat, EY hat, EZ hat, del X, del Y, del Z. X component is X minus Y component is X plus Y, Z component is 0. Now, performing this determinant with respect to the first axis here, I cross out the first row and first column. Del del y 0 is 0, minus del del z x plus y is 0, so 0 times ex hat. Then I cross out the first row, second column, del del x 0 minus del del z x minus y is 0, so 0 times ey hat. And finally, I have this ez hat term. So let me work on this term here. And this is going to be del del x plus y minus del del y x minus y. So this is in ez hat direction. I have del x plus y minus del y x minus y. So the first derivative will be 1. So in ez hat parentheses I have 1. The second derivative is minus 1. Minus 1 is plus 1. So therefore the answer is 2 ez hat. Okay, now why is this important? Going back to the previous problem, we have shown that curl of a gradient is 0. So if the curl is non-zero, that means it cannot be written as the gradient of something. So since we know that the curl of a gradient is 0, the curl of f being non-zero implies f cannot be written as minus the gradient of a scalar potential. This is an important result. Okay, so we worked on the work done by a force F given in this form from point 11 to 33, first on a straight line path where x is equal to y, so this term disappears and we have 2y ey hat, and then from on a second path from 11 to 13 and 13 to 33. And we have shown that the work done by this force for these two paths between these endpoints is different, which means the work done by the force depends on the path taken. F is a non-conservative force. It cannot be derived from a scalar potential. The answer doesn't depend on the endpoints only. It also depends on the path taken. So this shows that F is a non-conservative force. Checking the curl of F and finding that it is non-zero also implies that the force F cannot be written as the minus gradient of a scalar function, because curl of a gradient is 0, as we have shown in the previous problem. And so basically we find that there are two ways of showing that a force is non-conservative, by showing two paths on which we find the work done being different, and also checking the curl of F and finding that it is non-zero.